When a function is not continuous at a point, we say that it is discontinuous or has a discontinuity at that point. In this case, we are looking at x equals a. The three types of discontinuities are jump, removable, and infinite. You can see what each one looks like here. A jump discontinuity almost always occurs with a piecewise function. The limit does not exist, although the function may still be defined at one of the one-sided limits. A removable discontinuity is the easiest to quote-unquote fix. It almost always occurs with a rational function. And a removable discontinuity, we can see that the limit still exists at a, however, the function is not defined there. It's a hole. And lastly, an infinite discontinuity is when we have one-sided limits going to positive and or negative infinity, but the overall limit does not exist and there's a vertical asymptote there. Here is the main synopsis of the explanation behind each one of the three types of discontinuities. For this rational function here, let's find and classify any points of discontinuity. Well, just from math in general, we know that when we have a rational function with x in the denominator, we do have a potential for issues because when the denominator equals 0, then we have a potential point of discontinuity. What we need to do is figure out when the denominator equals 0. So let's take a look at our denominator here. It is a quadratic, and so setting it equal to 0 gives us a couple options to solve. This is factorable, but you could always use the quadratic formula as well. So when we factor it, we see that we have two factors, of course, right? It's a quadratic. So what I'm simply going to do is rewrite this quadratic in factored form to see if anything cancels or simplifies top to bottom. We do already know, looking at this, that the 2 points of discontinuity are going to occur when the denominator equals 0. So at 3 and 1, we do have 2 points of discontinuity. Now, which type of discontinuity depends on whether or not we can cancel any factors. So again, we have 2 points of discontinuity, the two values that make our denominator equal to 0. And then in order to classify each one, we simply just see if the factors will cancel or not. So again, the three types of discontinuity: jump, removable, infinite. A jump discontinuity is not going to be occurring here. This is not a piecewise function. So we essentially need to know, is this going to be a removable, which is a hole, or is it going to be a vertical asymptote, an infinite discontinuity? Well, since nothing canceled with the x plus 1, both of these are infinite discontinuities. They're both vertical asymptotes. Let's take a look at the graph of this just to make sure. Looking at the graph on Desmos here, I did plug it in factored form, but you could have plugged it in its original form as well. We can see that we do have a vertical asymptote here at 1, and we have another vertical asymptote over here at x equals 3. We can see that the one-sided limits go to, positive and negative infinities at each one of these asymptotes, and then therefore the overall limit at each one of these discontinuities does not exist. So both of these are infinite discontinuities, which graphically are vertical asymptotes because there were no canceling of factors. This next example is super similar. So our first step, once again, is going to simply just be to factor our denominator. It's the same denominator, so nothing new. So again, the 2 points the two x values that make our denominator 0 are 1 and 3, once again, and so those are our 2 points of discontinuity. Writing out this rational function in factored form looks like this. So again, this function is super similar to the previous one, except now we can see that our numerator is now x minus 1 and therefore cancels with this factor here, the x minus 1s. So since we can cancel those, that means that this discontinuity right here is now a hole. It's a removable discontinuity. This is really, in simplified form, the function 1 over x minus 3 that is just undefined at 1. There's actually a hole there. So at x equals 1, we have a removable discontinuity. And at x equals 3, because this did not cancel, just like in our previous example, we still have an infinite discontinuity there. Let's take a look at the graph just to be sure. Looking at Desmos, we can see that this function does have a vertical asymptote like we said at x equals 3. That's that infinite discontinuity. However, at x equals 1, we have a hole there. Now, this hole is so small that we can't actually see it on the graph like this. However, we can take a look at a table of values just to be sure that the function is not defined at x equals 1. Taking a look at the table, we do see that at 1, our function is undefined there. There is a very, very small hole. Now, what is the y value there? What would the function have been if we had canceled this? Well, previously, we just said that this function, when the x minus 1's cancel, it simply was 1 over x minus 3. Well, let's plug in what that theoretical x value would have been at 1. If we plug in a 1 here, we'll have 1 over 1 minus 3. And so our hole is at 1, comma, if we plugged in 1 here with the canceled form, 1 over x minus 3, 1 minus 3 would be negative 2. We'd have negative 1/2. So that's technically where the hole is, right there. All right, let's take a look at this one here. We want to find and classify a point of discontinuity. Well, this is a piecewise function. We could graph it, and you can definitely graph this in Desmos. But if we want to just take a look at where would the potential point of discontinuity be, it's clearly at 2. 2 is the breaking point of this piecewise graph. The functions are pretty tame. This is not a rational function. This is 1/2 x. This is a line. This is the coordinate point 2, 2. That's where the function's defined. And then this is simply a line to the left of 2. So none of these functions on their own have any points of discontinuity. They're just lines and a point. However, at 2, we need to double check that the limits equals the function value. We're going to go through our continuity checklist at 2. So our question is x equals 2 a point of discontinuity, or is it continuous there? Our first step is to find the limit as x approaches 2 of our function. And we need to look at the limit from the left and the limit from the right to determine that. The limit as we approach 2 from the left would be looking up here, 3 minus 2. So the limit from the left is 1. The limit as we approach 2 from the right, we need to look at the bottommost function since that's to the right of 2. If we plug in 2 here, we will get 2 over 2, so we also get 1. All right, so the limit exists and it equals 1. The second step is to double check the function value at 2. So what is the function value at 2? Well, when x equals 2 exactly, the output is 2. Even though both of these things are either exist or are defined, they do not equal each other. So they're not equal to one another. Therefore, we're discontinuous at 2. So x equals 2 is our point of discontinuity. I made a quick sketch of this piecewise graph. Here is the line 3 minus x, y-intercept at 3, slope of negative 1. That occurs to the left of 2. So here's x equals 2. Then at 2, our output's 2. And then 1/2 x is just a line that would theoretically hit at the origin, up 1 over 2, up 1 over 2, and so on. So that's our linear function there. We can see that the limit is in fact 1, but the function value is 2. This could be classified as either a jump or a removable discontinuity. This is one where either one would be okay because the limit does exist, but also this function is defined up here. So you could honestly classify this as either one because it is pretty easily removable. If we just change this to a 1, then we would be continuous there. So it's very easy to remove, but also technically you could call it a jump. So either or is fine here, but it's clearly not an infinite discontinuity. Go ahead and try this practice problem. Pause the screen and then hit play to see the answer. Turns out there's a jump discontinuity at x equals 0. For a little bit more explanation about the piecewise function, I suggest that you take a look at the last example again. However, our limit didn't exist at that breaking point 0. That means that the function is approaching two different y values, to the left and to the right of 0. 1 and negative 3. So the overall limit does not exist. If we think about what each one of these looks like, this is simply a parabola or part of one, and this is just a line. So no weird things going on anywhere but x equals 0, potentially, and so we don't have to check out any other points. Here is a quick rough sketch of the piecewise function. We have the breaking point at x equals 0, or equal to here on this left side. This is simply just a parabola, x squared, parent graph shifted up 1 unit, and then this is just a line with a y-intercept at negative 3 and a slope of 1 that occurs to the right of 0 but not at 0. So we can clearly see that we have a jump discontinuity, and if you sort of think about what that means without graphing it, if you want to sort of think about it in your head, we know that since the left and right-sided limits were different, there was a jump there.